Well, looks like everybody's back, so might as well get back into this. So we left off right at the very bottom of this page. And page 3, rather abruptly, is talking about something completely different. For those of you who took the first course with me, you have already seen exactly the same page, right down to the same comma, at more or less the same point in Physics 121, about an hour and a half into the course. The question always comes up. Got this turned at kind of a funny angle. Question always comes up, how should you round off your numbers? Well, you know, that can be made into kind of a long story. And as I said last fall, I don't really want to invest the time in telling that long story and making you, well, the biggest part of the time would be making you practice it until you got good at it. And there are just other things I would rather spend the time on. So there is a right and a wrong way to round off your numbers. And I have summarized that in this densely spaced page of stuff here. But the part of it that matters to your grade anyhow is just simply that I expect you to be within 2% of the correct answer. If the correct answer is 1.0, or if the correct answer is 1.47 and you round it off to 1, that's 47% off, and that's too much. But if rounding off your numbers makes a difference of 2% or less in your answer, I'm going to treat it the same way as a spelling error. If you spell physics with an F instead of a PH, I may kind of shake my head and mumble something about you being ignorant, but I'm not actually going to take any points off. And in a similar kind of way, if the answer is supposed to be 1.47, but you write down 1.472896790042, however, you know, half a page of that, I'm going to look at it and say, you know, this person is just nuts, but I'm not actually going to take any points off. So as far as purposes of this course go, it's probably better to carry too many digits than too few. But what I really have in mind is 3 significant digits. Like the stuff that I've already got on the, you know, that I already went over here. 0.608, 3 significant digits. 5.39, 3 significant digits. 8.99 trillion or billion, 3 significant digits. So I'm looking for answers, that, at least in the tests and the homework, answers that are rounded off to 3-digit accuracy. In the lab, sometimes more or fewer digits might be appropriate depending on the accuracy of the measurements you're taking, but well, I probably won't say too much. If just don't round things off so that it makes a lot of difference in the answer. Don't throw yourself way off by rounding away too many digits. And if you're feeling ambitious, read through this and try to do what it says there. The reason for having rules like that is so that you don't deceive people about the accuracy of a number. If if you're measuring the length of this little box and you write down that it's, how long is it anyhow? Just to have it right side up. Say you write down that it's 9.38241 centimeters. Well, you know, they think you must have measured it with some really super accurate micrometer or something like that. And no, you just measured it with a ruler, but then you did something in your calculator and you just wrote down all the digits on the calculator, but you don't know it to the nearest millionth of a centimeter. Write it down that way, it looks like you do. And that's the reason for having rules for how to round the numbers off. But back to the main thread of our story here. I'm going to do another example, and you're going to do something kind of like it. So I believe this first one is called number, I think that's number 4 on the renumbered version of this. Probably be looking at it. Yeah. So it's a continuation of problem number, well, was this one? Where'd it go? Did I erase it? I must have been written here before. Gotta move the camera. I think it's gone off the chalkboard here, but it should still be in your notes somewhere that you had a 3, which side is that on? A 3 microcoulomb charge, and it was being pushed to the right. So the magnitude of the electric field, in other words, just how strong is it? I'll get to the direction in a minute. The magnitude of the electric field is the force per unit charge. And like we were talking about during the break, I think it's best, least likely to confuse anybody if you make the magnitude and the direction into 2 separate questions that you consider one at a time. So how big is it? Then which way does it point? So how big is it is a positive number. That's why I stuck absolute values on there. The answer to the previous question was 2.7 newtons. The amount of charge that felt that force was 3 times 10 to the negative 6 of a coulomb. So you divide that out and it comes out an even 9 times 10 to the 5th. The unit on it would be newtons per coulomb. Including the direction, so I'm not done yet. Well, I guess it was on the left. Yeah. Example number 1 is what we're looking at. And what was actually there was a negative charge. But the direction of the electric field is the direction of the force on a positive charge. So if a plus charge had been there, then if a plus charge, the actual question, a negative charge was there and it was attracted, but if a positive charge had been there, it would be repelled. The direction of the field is the direction that a positive charge would get pushed if it was located there. So the direction of the electric field vector at that point, the electric field due to this, I guess it was 4 microcoulombs over here. The direction of the electric field coming from that 4 microcoulombs is toward the left. And what I want you to do is this question here, this number 3 that's still up on the board here, do the same thing with that, okay? Find the electric field at the location of the 2 microcoulomb charge. And then in part B, what if it would have been an electron there instead of 2 microcoulombs? Let's pause for a moment. The answer to part B that I didn't have written there is that it's exactly the same as part A. If you're out there furiously calculating something for part B, you can just stop. The idea is that the electric field is a property of a point in space, which doesn't really have anything to do with what's occupying that point, okay? It's just like a gravitational field. The electric field vector, you've got force per unit charge. The gravitational counterpart for that kind of thing is the gravitational acceleration. Everybody remembers weight equals mg, maybe? Well, not everybody, but at least the ones who took Physics 121 from me within fairly recent memory. G is, 9.8 for the Earth. It's something like 3.7 or 3.8 on Mars. It's something like 1.6 on the Moon. That's how you describe the strength of the gravitational field you're in. Well, weight means the force of gravity. I could just as easily have used the letter F instead of W. The gravitational acceleration, 9.8 near the surface of the Earth, is the force per unit mass. Well, mass is to gravity what charge is to electricity. You get a bigger charge, it's got a stronger electric field around it. You get a bigger mass, it's got a stronger gravitational field around it. So force per unit charge, force per unit mass, same idea. Now, at this point, right in front of my nose here, G is equal to 9.8. Whether I put a paper clip there, or whether I put a 50-pound bag of potatoes there, or whether I put nothing at all there, if it's just an empty point in space, that's the strength of the field at that point. And it's the same thing here. Whether it's a positive charge, whether it's a negative charge, whether it's a big charge, whether it's a small charge, the field at that point is the field at that point. And once you've calculated it in part A, you know what it is, and you can just write it down again for part B, and that's all there is to it. So I should do part A. I guess this is number 4. Got it right here. Yeah. Force per unit charge. To get the magnitude of the field, you want everything positive. So, well, in this case, it's a positive charge, so I didn't really need the absolute value signs. But as we saw back here when you did number 3, if there is a 2 microcoulomb charge at that point, then that charge will feel a 5.39 Newton force. So 5.39 newtons. 2 times 10 to the negative 6 coulombs, 2 microcoulombs. And so that divides out to 2.70 times 10 to the 6 newtons per coulomb for its magnitude. As for its direction, well, this 2 microcoulombs felt a force toward the left, and that 2 microcoulombs was positive. The field points in the direction of the force on a positive charge, so that would also be to the left. And then, let's see, that was part A. As I just said a couple minutes ago, the answer to part B is the same as the answer to part A. Well, the next part of this basically takes Coulomb's law and breaks it into 2 steps. Step 1, you've got 2 charges like we had back here in this question here. Step 1, one of these charges creates an electric field around itself. Step 2, the other charge feels a force because it finds itself in that field. So E is force over charge. If you stick the formula for Coulomb's law in for the F in F over Q, then one of the Q's cancels out, and you're left with just E equals the Coulomb's law constant times KQ over R squared. That would be the strength of the electric field around, well, I should probably have emphasized this a little more earlier. Coulomb's law works around a point-like charge, such as an electron, for example. A point-like charge seems like a bit of an approximation or an abstraction, and quite often it is. In the case of an electron, though, nobody has ever been able to measure the radius of an electron. It seems unlikely it's truly got a radius of 0, but however big it is, it's smaller than we can measure with our current technology. So for all practical purposes, yeah, an electron really is a point particle, at least within our current ability to measure. So for something like that, Coulomb's law works. Or for an electrically charged sphere, like if you took a basketball and rubbed it around on your hair real good and got charge evenly distributed all over the whole thing, the field outside of that would be given by Coulomb's law, where R is the distance from the center of the basketball. For other ways of distributing charge, like when I had this charged rod, yeah, actually Coulomb's law doesn't work for that unless you're so far away from it that you can think of the whole thing as being located at a single point to a good approximation. So anyhow, this gives the electric field around some point-like charge, like an electron, or at least something that can be approximated as located at a single point, like something that you're very far away from. It also assumes that it's in a vacuum as opposed to an electric field in some material like glass or plastic or something like that. So step 1, one charge creates this electric field around itself. The strength of the field drops off as the inverse square of the distance. If you get twice as far away, the field is 1/4 as strong. Step 2, you place another charge in that field. The force it feels will be F equals Q times E. that's just E equals F over Q rearranged to solve it for F. And I've got some examples coming up on the next page, but first of all, a little bit about how to draw pictures of electric fields. Of course, you can't literally draw a picture of something that's invisible, but the way it's usually represented is by using what are called lines of force. You just draw a bunch of arrows in the region that you're interested in, and those arrows all point in the direction of the electric field vector. So the field around a positive charge, for example, if I had this little ball here and I charged it up positive and wanted to draw a picture of the field around it, well, if I had some small positive charge to explore the field with, if I put that little positive charge here, which doesn't show up on the screen, but well, it would be pushed that way. If I can get that on the camera. Yeah, that kind of shows up, doesn't it? That's not so bad. It's actually a little better than when I used to try and do the same sort of thing with the smart board in the other room. If I put a proton, for example, there, it would get pushed that way. If I put a proton there, it would get pushed that way, and so on and so on. Positive repels positive. So the field points radially outward away from the charged object that's creating the field. Another example. What if I charged up this ball negatively? Well then, if I had some small positive test charge, a proton perhaps, if I put a proton there, it would be attracted to this negative pith ball, so the field would point that way there. If I put a proton here, it would be pulled that way. If I put a proton here, it would be pulled that way, and so on. So field lines point toward a negative charge. In a more complicated situation where the field is the result of multiple charges, like here you've got, oh, you don't really have to know the name, but it's called an electric dipole. You've got a pair of equal and opposite charges like that. If you put a proton here, it would be pushed in that direction being tangent to this, well, we call them field lines, but in a more complicated case like this, they actually curve. They aren't straight lines. Direction of a positive charge placed here be along a tangent to the field line. These pictures not only show you the direction of the field everywhere in the region that you're drawing, but also show you, if you know what to look for, they show you the relative strength, because where the lines get close together, the field is stronger. Where the lines are farther apart, the field is weaker. Like around this charged pith ball, for example, the field drops off as 1 over r squared, meaning farther away you get, the weaker the field is. Well, the farther away you get, farther apart the lines are. So the density of lines shows you the strength of the field, and the arrows that you have on them show you the direction of the field. So here's one where I want you to draw a few pictures. 4 different situations. In each case, draw an arrow at point P in the direction of the electric field at that point. Well, the thing to keep in mind for all 4 pictures is that I'll write it down. Field lines point from plus, in other words, away from positive charges, toward negative charges. Field lines run from plus to minus, and at any given point, the field is tangent to the field line. put line in quotes because, you know, like in part D there, those are pretty curvy lines. We're calling them lines. So in part A, there's a plus charge over here, and you want to know the direction of the field at that point down there. Well, the field points directly away from a positive charge, so that would be in that direction. Part B, got a negative charge. Question asks, what's the direction of the field over here? An electric field points toward a negative charge, so you would draw an arrow that points that way. For part C, now you've got something like a set of parallel metal plates, which have been given equal and opposite charges. And at a point in between those, well, the field points, like I wrote back over here, it points away from plus and toward minus. So the field would point horizontally like that. And in part D, you've got these curved field lines, in this case produced by some charges that are beyond the edge of the picture someplace. And the question is, what is the direction of the field at that point right there? Well, tangent to the field line at that point, right there, a tangent would be horizontal. So you want to draw an arrow that looks something kind of like that. And then this is the last page for today, but it takes a little while. Superposition principle. Like back here on this page, where there was the field due to both the plus and the minus. What's the combined effect of these two at this point over here? Well, what you have to do is you have to figure out the electric field coming from the one charge and the electric field coming from the other charge. And what you get with both of them at once is the vector sum of those two individual fields, which in a situation like this, back here in page 4, that would be all the thing about components and sines and cosines, and like I promised you I wouldn't do this time around. So let's just stick to examples where everything, we'll just stick to examples where everything is along the same line. I ought to be keeping my microphone closer to me. But whether it's just a one-dimensional problem like this or two-dimensional problem like the one on the previous page, if you want to know, well, for example, in this one that I'm going to do here, find the force on the 3 microcoulombs, the one over on the right. What you do, probably turn that over that way again. Find the force on this one. Well, first of all, just pretend the 8 microcoulombs isn't even there. You've got this -5 and you've got the 3. Use Coulomb's law, figure out the force on the 3. Once you got that written down, now you pretend the other one isn't even there. Use Coulomb's law to figure out the force on the 3 from the 8. The total force with both present at once, add them together. That's the superposition principle. And I'll write that all out in a moment. The idea is I'm going to do this one, I'm going to do this one, and then you do this number 4 here. Well, except I think it's like number 9 on the copy I made. I really have to make some new transparencies, but like I said, I want to see how the recordings come out. Similar sort of idea, find the electric field at point P, which is just a point in space. I mean, there may or may not even be anything located there. The electric field, like a gravitational field, is just, you know, it's there whether there's something to feel its effects or not. So you have to find the electric field from the -4, you have to find the electric field from the +5, and you add the two of them together, and that's how you do that. So that's kind of the overview. And as for the details, details go like this. So I thought what might be a good notation is to say that the force from the 5 microcoulombs, I thought I'd call that F5, as in the force from the 5 microcoulombs. The force on the 3 because of the 5. Coulomb's law. 8.99 times 10 to the 9th times the product of the charges. I'm finding the force on the 3 microcoulombs, so that goes in. I'm finding the force due to the 5 microcoulombs, so that's the other one that goes in. And the 5 microcoulombs is 30 centimeters away. Convert that to meters, 0.3 of a meter. That gets squared. And what I kind of like to do sometimes is carry an extra digit and then round off when I get to the answer. That way I don't make any noticeable rounding errors. So 1.498 Newton, roughly 1.5 newtons for the magnitude of the one force. And then there's the force coming from the 8 microcoulombs. Same thing, except where the 5 used to be, I'll have an 8 instead. That one is 50 centimeters from the 3 microcoulombs. 30 plus 20, 50 centimeters from the 8 to the 3. And that comes out 0.863. So that's how big that force is. Now, before you add them together, you have to take the directions into account. So I'm going to make a little sketch here. There's my 3 microcoulombs. The force from the 5 is attractive. The The 5 is negative, the 3 is positive, opposites attract. The 3 is being pulled toward the 5. And I just figured out that that was 1.498 newtons. The force from the 8 microcoulombs, well, the 8 and the 3 are both positive, so they repel. The 3 is being pushed away by the 8. So that's an arrow in that direction. And I drew it a little shorter because 0.86 is smaller than 1.49. So the way that directions are usually included with the numbers is that usually you say right is positive and left is negative. So that's going to be, you see, well, in this case, it probably would have worked out. Sometimes people stick the minus sign up in here on the cue, and in this case, that would have worked out all right. But if I'd made the question a little different, sometimes people get messed up with the directions. My advice is to keep the magnitude and direction two separate questions. Throw away all the minus signs, figure out how many newtons, then consider the pluses and minuses and what the directions have to be. Don't get distracted by any, if this comes out negative because you didn't use the absolute value signs. Anyhow, we've got 0.863 pulling to the right, or pushing maybe is a better word, pushing it toward the right. We've got 1.498 pulling it toward the left. Superposition principle says to add those together, the positive number and the negative number, and it comes out 0.635. That's measured in newtons. And the significance of the minus sign is that the overall effect is toward the left. If you were to release the 3 microcoulomb charge from that position, it would move toward the left. The bigger force is going to win. The next problem is similar, except it involves the E vector instead of the force. Just a variation on the same idea. Find the electric field at point P. Electric fields point toward negative. Here's point P. Electric fields point toward negative charges. So the electric field from that 4 microcoulombs points toward it. Electric fields point away from positive charges. So the electric field from the 5 microcoulombs points away from it. So just like when I had you drawing pictures back over here, where that's coming from is the idea that electric fields point from plus charges and toward negative charges. As for the magnitude of each of those, like it said somewhere on the previous page, the electric field around a point-like charge or around a sphere It's the Coulomb's law constant times Q over R squared. The field from the 4 microcoulombs we've got 4 times 10 to the negative 6 for the charge. And it's 0.1 of a meter away from point P. And squeeze that in there. Put it down here. 3.596 times 10 to the 6. And as it shows on the sketch up there at the top, that points toward the right. The other one, the 5 microcoulombs is 0.2 of a meter away from point P. And like I sketched up here, it points to the left. If right is positive and left is negative, you're going to be subtracting those numbers. Rounding off a little bit. 3 significant figures. .5 something minus 1.1 something gives you 2.4 something times 10 to the 6. And since it comes out positive, the overall effect is toward the right. So the one thing I still want you to do this afternoon is to try number 4 for yourself. Since we still got, you've got more than enough time to do that problem. Maybe I'll take care of 1 or 2 things so we don't have to worry about them next time. Next time we will do the first lab. Well, there's been an emphasis on laboratory safety for a number of years now. There's a little form that you're supposed to fill out and sign saying that you've been made aware of certain things, and I'm going to hand you this little form. Here, let's hand it out, and I'll briefly go over it, and then you'll sign it, and then I'll put it in my files for 3 years, and then I'll throw it away. If you've taken any other science courses at this college, you may have been given a similar form to sign, except that it had like 75 things on it and was 2 or 3 pages long, and I kind of abbreviated that down. I don't think it makes any sense to alert you now about some way that you might hurt yourself 2 or 3 months from now. So I'm just going to say that there are safety warnings incorporated into the instructions for labs where I'm trying to think of ways of hurting yourself in this course, actually. Usually we work with fairly low voltages or other well, I don't know. I'd have to sit down and flip through the whole lab book. But if, like it says at the beginning, the most dangerous thing you're going to do for this course is riding a car getting here. But there may be a few hazards now and then. You should read through the directions for the experiment before coming to class so that you've been alerted to any ways that you might possibly be able to hurt yourself that day, even if it's just dropping a heavy weight on your foot or something like that. You should also read through the experiment before you get here because you'll get out of here quicker that way, as opposed to sitting there and reading it during the lab period and figuring out what's going on if you already know what's going on. Because I know that most people's goal for the afternoon is to get out of here. So it says, it is the student's responsibility, that's you, to read the current exercise before coming to the lab and being aware of any cautions or warnings. Also, number 2, if I think of something to say during the lab, here's a surprise, you're supposed to listen to me. So pay attention to any additional instructions I may give verbally. Number 3, inform me if you have a medical condition that could affect your ability to do the labs. There again, I'm having trouble thinking what that might be, but you know, it's a big world, a lot of things going on in it. Number 4, are there any labs where we use glassware? Well, hypothetically, if we used glassware for anything, we did a couple times in the fall semester. If you break something, let me clean it up, because if you prick your finger, then you're going to go to an attorney and they're going to try and sue us for $500,000 for pain and suffering. And do not throw broken glass into waste baskets. If you insist on cleaning it up while my back is turned, there's a place up in the chemistry lab where I'm supposed to take broken glass. Don't just throw it in the waste basket. Report any injuries to me, no matter how trivial they may seem. And if you are confused by the directions at any point, don't just make stuff up. Have me explain it to you, because like it says here, on rare occasions, a student may find a novel way of causing injury that I did not anticipate. As the expression goes, nothing is foolproof because fools are so ingenious. So just because I think there's no way of hurting yourself doesn't mean that, you know, somebody won't try and swallow their calculator or something like that and choke on it. So if you need any clarification, please do not hesitate to ask for it. And having said that, I think I've covered everything that I'm supposed to cover. And yeah, got them all done. And I'll have a few more introductory comments to make at the beginning of the lab on Wednesday, but let's leave it at that for now. So work your way through number 4. When everybody seems to have had enough time, I'll go over it. You may or may not wish to wait that long. There were a couple of times last fall when I found myself for the last problem of the day, there was more than once I found myself standing here talking to an empty room because I wanted to get it in the recording, but all the students had left because they all had it right and they didn't feel like waiting around. So it's up to your judgment when you head out the door. But once you've gotten, well, I guess I do need to tell you what the answer is for part B. I left it out because I didn't want to give something away. So it goes like this.
Is that okay if we go? Okay.
Thank you. Yep. So here's charge A. sitting here over on the left-hand side of the picture. And charge B pulls on it because they're opposite charges. So the force from B is that way. Force C pushes on it because they are like charges repel. Calculate each individual force. It's kind of like, you know, you've got two people pushing on this chair, one pushing that way and one pushing that way. It's just they're invisible people this time. But the forces add up, you know, they superpose the same way. So 8.99 times 10 to the 9th. Since it's the force on A, force on A from B, I want to write down the charges of A and B. 2 times 10 to the negative 6 and 3 times 10 to the negative 6. They're separated by 0.1 of a meter. That comes out 5.39 is probably good enough, but I went one more digit with it, just to be kind of obsessive compulsive. Toward the right. Force on C, I want the charges of A and C in this. They are 0.2 of a meter apart. This is going to be one of these things where I end up talking to the empty room, isn't it?
Yeah.
Yeah, well, I want the recording to be complete, you know, so. Total. One of you might get an urge to play this back when you're studying for the final or something like that.
Have a good night.
You too. Since it comes out positive, the direction's to the right. I should have labeled that as being part A. For part B, what is the net force on the one in the middle? Well, you could write all this sort of thing out again. How many newtons is the one force? How many newtons is the other force? And then put them together. But if you kind of stop and think about it before you get lost in the details, in part B, these are going to come out the same number of newtons, because both charges, A and C, are 2 microcoulombs. They're both 10 centimeters away. So same amount of charge at the same distance is going to create the same amount of force with opposite directions. And so they just cancel. The answer is 0. There's the negative charge. Force from C is that way. Force from A that way. You've got the same charges, the same Q's and the same R's, same charges and the same distances. So the forces, the F's, are the same size, opposite direction. So they cancel out, total is 0. And we're done 10 minutes early, even talking to an empty room.